Krishna 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 Krishna.
Good morning. I am Dr. Ravi M. Medhaldi, Professor and Head of the Department of ENCE, SG Balekandri Institute of Technology, Belgavi. Today let us see what is bipolar junction transistor. So in this particular the syllabus covered will be the operation. We will be discussing about the operation of the bipolar junction transistor, and also let us know the BJT voltages and currents, and also we will be able to discuss the amplification process of the BJT. In addition to this, we shall see the common base characteristics, common emitter characteristics, and common collector characteristics of bipolar junction transistors. And at the end of the 3 days, we shall have we shall solve some numerical examples. Prior going to this, discussing about the bipolar junction transistor, let us review what we have discussed in the last week. As you know that the semiconductor diode, it consists of the P layer and N layer. When these P layer is joined with N layer, then the majority charge carriers in the P layer, that are holes, they will start moving from higher concentration area or region to the lower concentration area, that is P to N. Similarly, on the other hand, the electrons, they move from the N region to the P region. When the holes from the P layer, they come on to the N layer, then they neutralize some of the electrons. Similarly, electrons, when they move from N to P, they neutralize holes on the P region. So that will create, this neutralization process will create a layer that is called as the depletion layer, or also it is called as the depletion region. As I told you earlier, the depletion region, it doesn't consist of any free charge carriers. It only consists of the immovable fixed ions. As you can see here, we have a P region having the holes as the majority charge carriers, and the minority charge carriers will be the electron. Similarly, you can see here the N region consisting of free electrons as the majority carriers, and in between this, there is a region forms that is consists of fixed, that is immobile ions. So you can see here on the left side the negative ions, on the other side you can see the positive ion. And this layer, and because of this layer, there exists a barrier potential. It is also called as the barrier voltage. So the creation, the existence of the barrier voltage will it will avoid, or it will not allow the free movement of the charge carriers. So also we have seen the two types of the biasing techniques, that is in the case of semiconductor junction diode. In the case of the forward biasing, you can see that the P layer is connected to the positive terminal of the battery. Similarly, N layer, it is connected to the negative terminal of the battery here. So that is called as the forward bias, and due to that you can see that the holes, that is the holes in the P layer, they will get repelled by the positive terminal of the battery. Similarly, the electrons in the N layer, they get repelled by the negative terminal of the battery, and therefore they will cover this depletion layer, and therefore the width of the depletion layer decreases, and accordingly the potential barrier decreases. After a certain time, that is when the battery voltage reaches the threshold voltage or cut-in voltage, which is 0.7 volts in case of the silicon diode, and it is 0.3 volts in case of germanium diode. The completely the this particular depletion layer, right, it will be overcome, and therefore there will be a free movement of the charge carriers across the PN junction diode. As you have seen in the mainly in the reverse biasing, right, the negative terminal of the battery here it is connected to the P layer, and similarly the positive terminal of the battery it is connected to the N layer. And due to the application of this negative potential, the holes in the P layer, that is this, okay, and similarly the electrons in the N layer, they will be attracted by the battery voltage, and therefore the result is the increase in the width of the depletion layer, and therefore the potential barrier will decrease. So therefore there will be no movement of charge carriers in the semiconductor diode. So but however there will be free, the movement of the minority charge carriers will be there, right, when the semiconductor junction diode is reverse biased, and the magnitude of this minority charge carriers, it is very less, that is in the range of microamperes. So then we shall see about the mainly in this session. At the end of this the session, you will be able to the acquainted with the construction of the BJT, that is bipolar junction transistor, and also understand the BJT operation, know the BJT voltages and currents, and also you will be able to distinguish between the active, cutoff and saturation region. As you know that the bipolar junction transistor, it is invented in the year 1948 by Bardeen, Brattain and Shockley, and the bipolar junction transistor means it is in short it is called as BJT. The term bipolar, that means bi means there are two, polar means the charge carriers, that means the conduction in the BJT, it is due to two types of charge carriers, that is holes as well as the electrons. So whereas the junction means the semiconductor, this BJT is having two junctions, one is the base emitter junction and other is the collector junction or collector base junction. Whereas the transistor, the term transistor, it signifies the transfer plus resistor, that means the transfer of resistance from low resistance region to the high resistance region. Friends, you know that the BJT, it consists of two junctions, one is emitter junction, another is collector junction. Emitter junction is usually forward bias, whereas collector junction, it is normally reverse bias. So therefore when emitter junction is forward bias, it will have a low resistance region. When collector junction is reverse bias, it will be having the high resistance region. So when we apply the signal, so that will be transferred from the low resistance region to the high resistance region. That is why it is called as transfer of resistor, transfer of resistance, or in short it is called as transistor. And the BJT, the bipolar junction transistor, it is used as amplifier and as well as the logic switch. So when this particular bipolar junction transistor, it is used as logic switch, you can see that, okay, mainly. So we can have such a circuit that is shown in this particular slide here. So now let us know what are the terminals of the bipolar junction transistor and types of the bipolar junction transistor. BJT, it consists of three layers. It can be either PNP or NPN. PNP, in the PNP transistor, N layer, it is sandwiched between two P layers. Similarly, in NPN, you can see that the P layer, it is sandwiched between two N layers. Apart from that, it has got this BJT, it has got 3 terminals. One is called as the emitter, the other is the collector, then the base. So therefore, the bipolar junction transistor, it has got 3 layers, either it can be PNP or NPN with 3 terminals. One is emitter, another is collector and the base. And also let us see the construction of the bipolar junction transistor. Friends, the bipolar junction transistor, it consists of 3 layers. One is the emitter layer, that is what you can see here. It can be, as I told you, that the bipolar junction can be of 2 types. One is it could be of NPN or it is PNP type. So this, whatever you can see here, this NPN transistor, it consists of 3 layers. One is N plus, then P minus, then N layer here. As far as the doping concentration is concerned, this is called as emitter layer N plus, it is heavily doped, whereas the P minus layer, it is called as the base layer, it is lightly doped, whereas the N layer, which forms the collector of the bipolar junction transistor, it forms the collector. As far as the width of the layer is concerned, the emitter is having more wider or the more width, whereas the P layer, it is very thin here, whereas the collector region or collector layer, it is having area in between that of the emitter and the base. So if you understand these concepts, then it will be very easy to understand the operation of the bipolar junction transistor. As I repeat, the bipolar junction transistor, it has got 3 layers, that is it could be of NPN or PNP type, and as shown here, the N plus layer, it forms the emitter, N layer, it forms the collector, P minus layer, it forms the base here. And usually the N plus layer, it is highly doped compared to the base and collector, whereas the base layer, that is P minus layer, it is lightly doped. So as far as the area is concerned, the base layer is very thin compared to both collector and emitter, and also you can note that the N plus layer, that is emitter layer, it is having higher width compared to other layers. So that is what you can see here. The collector doping, it is usually moderate, that is in the range of 10 to 10 raised to 11, whereas the base doping is slightly lesser, that is approximately it is in the range of 10 raised to 9. And as far as the emitter doping is concerned, it is very right on the higher side compared to the both base and collector. So that is given as 10 raised to 17 here. The transistor, the bipolar junction transistor, can be compared with a dam here. So you can see that whenever the gate of the dam, that can be equated to base, and this side of the dam, that is we can say it as collector. On the other side of the dam, we can equate it to the emitter here. When this base or when the gate is open, there will be a flow of water from emitter to the collector, or from other side to this side here. So similarly, whenever the base is properly biased, right, the current will flow from emitter to the collector here. So therefore, you can say that the BJT is almost it works on the similar line as that of the dam which is built on any river there. As far as the BJT currents are concerned, you can see that this is the symbol of PNP transistor, whereas this particular the slide or the symbol shows the symbol for the NPN transistor, where here as it is indicated, IC is the collector current, whereas IB is the base current, and IE is known as the emitter current. And whatever the arrow you can see here on the emitter, so please note that this arrow is always drawn on the emitter. So therefore here in PNP transistor, so arrow is exist here, therefore this is called as emitter. Similarly, you can see arrow once again on this terminal, so therefore you can simply using looking at the arrow, you can say that this is an emitter there. And also you should note that the arrow always pointed towards the N type here. In PNP, this is P and this is N and this is P. So therefore this arrow, it is pointing towards the N, that is nothing but the base region here. Similarly, in NPN you can see that this is NPN. So as I told you that always this arrow pointed towards the N type. So therefore this is, since it is NPN, so it will be pointed towards from, that is base towards the emitter here. So that is what you can note on here. So therefore this arrow, it always indicates the direction of emitter current. In the PNP type, it is the current, emitter current, it flow, that is indicated, that is towards the base region, whereas in NPN it is away from the base region here. So therefore in case of PNP, the current flows from emitter to base, whereas in NPN it flows from the base to emitter here. And let us have a look at the current and voltage equation in case of bipolar junction transistor. As it is indicated in case of NPN, this is NPN transistor, IE, that is input current, that is usually called as emitter current, that can be equated to IB plus IC there, or you can say that emitter current is sum of the base current and the collector current. Similarly, if you apply a KVL to this transistor, you can note that VB is equal to VC plus VBC. So from that we can say that VC is nothing but sum of minus VBC plus VBE. Similarly, in case of PNP, that is what the symbol is shown. If you apply the KCL to this transistor, PNP transistor, emitter current can be quoted to IB plus IC. That is, emitter current is the summation of sum of the base current and the collector current. Similarly, if you apply KVL to this PNP transistor, VEC can be equated to VEB minus VCB. Friends, you know that if you apply KVL here, VEB is nothing but sum of the VEC, this current, this voltage, sorry, and then the collector to base voltage here. So therefore VCE means in case of NPN, you can see that VC means collector to emitter voltage, whereas VBC means the base to collector voltage, whereas VB is base to emitter voltage. So this particular slide shows the equivalent circuit of BJT, that is in terms of the diodes, right. So here, as shown in this figure, the transistor can be equated to two semiconductor diodes which are connected in back to back fashion here. So therefore the conclusion is that if you want to understand the transistor, you should then, you should know the working of the diode. The understanding of the working of the diode is helpful to understand the operation of the transistor here. So as far as the biasing is concerned, so a single PN junction has two different types of bias, as you have seen earlier, semiconductor diode, right. So it has different types of the bias. One is called as the forward bias, the other is called as the reverse bias. So therefore the two PN junction device has four types of bias. A combination of that will result into that will define the region where the transistor is operating here. If the emitter base junction is reverse bias, so and collector base junction is also reverse bias, then the transistor is said to be in cutoff region. Similarly, so the transistor will be inactive whenever the emitter base junction, that is input junction, is forward bias, and collector base junction, that is output junction, is reverse bias. And as far as the saturation is concerned, in the case of whenever the saturation region, the emitter base junction of the bipolar junction transistor is forward bias, whereas the collector base junction is also forward bias. So therefore, combination of this, okay, biasing which gives rise to, right. So where exactly the transistor is operating here. So depending upon this the modes of operation of transistor, we can able to define the application of transistor. So usually the active region, it is being used for the amplification purpose, whereas the both cutoff and saturation, it is being used, right, for, right, whenever the transistor is operated as switch. So in this slide, right, the active region, right, it is said to be central to amplifier operation, right. So the region where the current curves are practically flat, right. So usually this, in this region, the, okay, the characteristics, the current characteristics or current curves, they are usually flat and there will be equidistance. So the distance between the current curves, it is equal. So that is the one important, right, the feature of this active region here. The, what is the feature? One is the current curves are practically flat, and also, right, so these, right, there will be equal distance exists between the, right, the neighboring current curves. As far as saturation region is concerned, here the barrier potential of the junction cancel each other, so causing a virtual short. That means the bipolar junction transistor, it acts as a on switch or closed switch. Similarly, in the cutoff region, the current will be reduced to 0. So here, as I told you that in cutoff region, the emitter junction, it is reverse bias, and in addition to this, the collector junction is also reverse bias, and this will, right, make, or this results in the 0 current in the bipolar junction transistor, and therefore the ideal transistor, it behaves like an open switch. Therefore, so whenever we would like to use transistor, that is BJT, as an amplifier, we usually operate the BJT in active region, whereas, okay, whenever if we want to use the BJT as a switch, then I will be making use of the cutoff as well as saturation. Cutoff means the device acts as an open switch, whereas saturation means the BJT acts as a closed switch. Now let us see, right, the what happens, okay, the BJT when it is in active mode. As I told you that active mode, it is defined by the type of biasing here. Here the two external voltage sources will set the bias condition for active mode. As I told you earlier, the emitter base junction, it is usually forward bias, whereas the collector base junction, that is also called as output junction, it is reverse bias. So this, since the EBJ, that is the emitter base junction, is forward bias, and CBJ, that is collector base junction, is reverse bias. So the transistor will be operating in the active mode. So that is what you can see here. This is we have considered a NPN transistor, and N is connected to the negative terminal of the battery, even so with reference to the base. Similarly, this N, which is nothing but the collector, so it is connected to the positive terminal of the battery with reference to the base. Therefore, emitter, that is base junction, is forward bias, whereas the collector base junction is reverse bias. This particular slide shows, okay, whenever this forward biasing, okay, of the emitter base junction take place, or when we apply the suitable voltage across the emitter base junction, so therefore emitter junction will be forward bias, and therefore as you know that, okay, when this emitter base junction is forward bias, the electrons will be injected right into the base from the emitter here. So that is what you can see here, okay. So as you can see, so this is the mainly, so here you have got an N region, okay, we have got a P region, right, which is sandwiched between two N regions. So that is will be the NPN transistor there. So when this N region is connected to the negative terminal of the supply voltage with reference to base, similarly, okay, then NP region, that is also called as the emitter base junction will be forward bias, and similarly here this N, it is connected to the positive terminal of the VCC with reference to the base here. So this will be reverse bias. So when this emitter to base junction, that is NP region, is okay for the forward bias, you can see that there will be a depletion region, okay, and here also we have a depletion region existing across the collector junction. But since the collector junction is reverse bias, whereas the emitter junction is forward bias, the thickness of the depletion region existing across the collector junction here, it will be more compared to the thickness, that is of the depletion layer, that exists across the emitter base junction here. So therefore, application of this forward bias or across the emitter base junction, it will inject, it will the electrons, and it will force the electrons to move from N to P region here. So that is what you can see here. So therefore, electrons will move from the N to P region, okay, and similarly the holes will move from the P to N region here. So but however, the electrons are the majority charge carriers in N region, the current contributed by the electrons will be more. That is why it is indicated by a big arrow compared to the current contributed by the holes, right. So therefore, hole current, it is in small, okay, therefore it is indicated by a small arrow here. But please note that the electrons, when you apply a forward bias across emitter base junction, so the electrons will move from N to P, similarly holes will move from P to N, right. So what happens here? So now the conventional direction current will be opposite to the direction of the electrons, and it will be in the same direction as that of the holes here. So that is what we can note down here. So now let us see once again. So when these electrons, when they come to this base region, so now these electrons will be minority charge carriers in base region here, because this is N region, this is P region. So when these electrons from N to P they move, so therefore these electrons will become minority charge carriers. And as you know that since this output junction is reverse bias, there will be a depletion region across the output junction, and due to that there will be a potential barrier. But when these electrons they move from the N to P region or the emitter to base region, so they will be act like a minority charge carriers, and this whatever potential barrier that exists across the collector junction, that will be favorable to this. Therefore, these electrons immediately they will shoot through this base region, and immediately they will move into the collector region, that is across the reverse bias junction. But however, some of these electrons which move from the emitter to base, they will recombine with the majority charge carriers in the base region, which is nothing but a p type region there. So electrons which diffuse across the base region to the collector base junction are swept across the collector base depletion region to the collector here. Therefore, here you can see that. So the IE is nothing but what? IE is nothing but IEN, that is emitter current due to electrons, plus IEP, that is emitter current due to the holes here. Okay, that is what is indicated. Usually, normally IEN will be more, so therefore compared to the IEP. So therefore, current contributed by the electrons is more compared to that due to the holes. Therefore, IE can be approximated to IEN. Similarly, you can see here the IC is nothing but sum of the ICN plus ICBO. That means the ICN, that is the collector current due to electrons, plus ICBO, that is called as the small reverse saturation current. ICBO means the collector current that is flowing from collector to base with emitter open. O stands for the open. So therefore, here collector to this ICBO is called as the current which flows from collector to base with emitter open here. So since this ICBO is very small, this can be neglected, and also IC can be we can say that IC is equal to the ICN. So now you know that IC is equal to ICN plus ICBO, and also you know that the emitter current is summation of the base current plus collector current. So therefore here if you assume that ICN is equal to alpha times of IE, so if you substitute here in this, so what happens here, IC will be equal to the ICN plus ICBO. ICN if you substitute here, ICN is nothing but it can be substituted by alpha IE, IE is nothing but IB plus IC. If you substitute and arrange it suitably, we will finally arrive at IC into 1 minus alpha equals to the alpha into IB plus ICBO here. So where alpha is defined as the ratio of the collector current to the base current, or nothing but it is also called as the common base current gain, because this base terminal it is common with reference to what, the emitter terminal as well as the collector current here, collector terminal, sorry. So now let us see the transistor operation one by one. Here we have considered only one PN junction of the PNP transistor. We have taken a PNP. P is having the holes as the majority charge carriers, whereas the N is having electrons as the majority carriers. So therefore in this figure, right, you can see that the PN junction, that is emitter base junction, is forward bias. So therefore, so what happens here, and when this emitter base junction is forward bias, there will be the depletion region, and whose width is very small. So therefore the majority charge carriers, once this application, this applied voltage exceeds the barrier potential, there will be a free movement of charge carriers from emitter to base, that is P to N layer. Similarly in this case we have considered a reverse bias junction of a PNP transistor, wherein the base, the collector is connected to negative terminal of the battery with reference to the base here. So therefore once these electrons, the electrons, they move from N to P to N, they will act like a minority charge carriers in the N layer, and for these electrons, the potential barrier, because of this existing depletion region, act like it will be favorable. Therefore immediately these electrons will be sucked into the collector region, and that will be contributed to the collector current here. So therefore, and as I told you that, so when the emitter to base junction is forward bias, there will be a depletion region, right, and when this base to collector is reverse bias, or collector to base junction is reverse bias, there will be a depletion region, but the thickness of the depletion region existing across the collector junction is more compared to that across the emitter base junction here. So now you can see that both the biasing potentials have been applied to PNP transistor. So therefore here you can see that a depletion region, a thin depletion region existing across the input junction, that is between emitter to base. Similarly a thick depletion layer exists between the collector to base, which is reverse bias, whereas the junction, input junction or emitter junction is forward bias. So therefore when both the biasing potentials have been applied to PNP transistor, the majority charge carriers, so what are the majority charge carriers in P type? That are holes. They will diffuse across the forward bias PN junction into the N type material there. So when these holes they move from P to N, so what happens, some of these holes they will combine with the electrons present in the N layer here. So therefore that will contribute to the base current. So therefore that only you can say that 5% of the electrons which move from the P layer to N layer will be recombined with the electrons in the N region, that is base region, and therefore that will contribute to the base current, and this base current, which is very small, that will be in the order of microamperes, and the remaining 95% of the holes, so what happens, they will be sucked to what, the collector region, because this holes, when they move from emitter to base, right, when these holes, they will act like a minority charge carriers, and whatever the potential barrier existing across the collector to base junction, that will favors this, and therefore easily these minority charge carriers, they will move from N to P, and these 95% of these charge carriers, which are holes, that will contribute to the collector current. So therefore majority carriers will cross the reverse bias junction. So right, because these injected majority carriers will appear as minority carriers in the N type material, that is nothing but the base layer here. So if you apply the KCL to the transistor, what you will get? The emitter current is nothing but summation of the collector current and the base current here. So IC, right, where IC is nothing but the collector current, it comprises of two components, one that is collector current due to majority carrier, other the collector current due to the minority carriers. That depend, the majority and minority carriers, once again it depends upon whether you are using a NPN transistor or a PNP transistor. Therefore IC can be IC equals to IC majority plus ICO minority. So where ICO is nothing but the collector current with emitter terminal open, that is ICBO. O stands for open, emitter. What is missing here? That is collector base, emitter terminal is missing. Therefore when emitter terminal is kept open, whatever the current flows between collector and base, so that current is called as ICBO, and that is also called as the leakage current, and which is negligibly small. So in this session we have seen, right, the construction of the BJT, right. So as I told you that the bipolar junction transistor, we defined what is bipolar junction transistor. Bipolar means the current is due to the two types of charge carriers, that is electrons as well as the holes. That's why the name, right, the term bipolar. And junction means this transistor is having two junctions, right. One is the emitter base junction, another is collector junction, whereas T stands for transistor. Transistor, as I told you that transistor refers to, it is transfer of resistor or transfer of resistance. Since okay, the signal, it is being transferred from low resistance region to high resistance region, right, it is called as the transfer of the signal from the low resistance region to the high resistance region. Because here usually the bipolar junction transistor, the emitter junction is forward bias, so whereas the collector junction is reverse bias, and therefore the what happens, since the emitter junction is forward bias, so it will provide a low resistance to the applied signal, whereas the collector junction, collector base junction is reverse bias, it will provide the high resistance to the signal. So since the applied signal, it is right transferred from the low emitter junction, the low emitter junction resistance, low resistance emitter junction to the high resistance collector junction, that is called as the transistor, transfer of resistor or transfer of resistance from low resistance region, that is emitter junction, to the high resistance region, that is collector junction. And also we have seen the right, there are two types of the transistor, one is the PNP, another is called as NPN. And also you know that as shown in the figure, we came to know that the transistor is having three terminals, one is emitter, another is base, and third is collector here. As far as the construction of the bipolar junction transistor is concerned, so it consists of, if you consider only P and P, here you can see that as it is very much evident from the figure that P layer is having more width, whereas N layer is having the less width compared to other layers. So therefore this point you should note on, that is, one is width wise, the information is P layer, that is acts as the emitter layer, it is having more width, whereas N minus layer, which acts as a base layer, it acts as a the less width compared to others. Similarly, on the NPN type, similarly N plus that acts as the emitter and P minus acts as the base, whereas N acts as the collector. Here also N plus, that is emitter region, is having more width, whereas the P minus, which is called as the base region, it is having lesser width compared to other. Apart from this area or width, one more thing you are supposed to know, that is P plus layer is heavily doped. Plus indicates that it is heavily doped. So therefore emitter layer is usually heavily doped, whereas N minus layer, that is which forms the base, it is lightly doped, and whereas P layer, no sign is being assigned to this, therefore this P layer, it is moderately doped here compared to this. So if you know this information, one is the information with regard to the width, and another is with regard to the doping level of the each layer, then it will be easy to understand the operation of the bipolar junction transistor. And also we have seen, right, the sum of the BJT voltages and currents, and this you can see that the symbol of PNP transistor, and this is the symbol of NPN transistor, right, as it is noted here. This is the emitter terminal, this will be base terminal, this is the collector current, and that current that flows through the collector, it is called as collector IC, whereas that flows through the base, it is called as the IB, whereas the one which flows through the emitter is called as emitter current. And please note that this arrow, it is always towards N type. So here this is P, collector is P, base is N, and emitter is once again P. Therefore here in this case always this arrow will be towards the N, and also you should note that it will be right arrow, the emitter terminal will be having always arrow here. So therefore from the symbol easily you should note that as soon as you can have a look at it, it should be noted that the terminal having arrow, it should be the emitter terminal. So therefore from NPN transistor we can write that if you apply the Kirchhoff's current law, I is nothing but IB plus IC. Similarly the VB is nothing but summation of collector to emitter voltage and the base to collector voltage. This can be further modified as VC equal to minus VBC plus VBE. Similarly in the case of PNP, the both voltage, the current and voltage equation remains same. So therefore here also once again the input current IE, that is emitter current, is nothing but sum of the base current and the collector current. Whereas on the similar line as that of the NPN, here once again the voltage equations, it could be written as VEB is nothing but summation of VEC and VCB. So therefore from this we can say that VEC is nothing but VEB minus VCB. So therefore VEC means the voltage exists between emitter to collector, whereas VEB means the voltage that is appearing across the emitter to base, whereas VCB the voltage across the collector to base. And also we have seen the three regions, operating regions of the bipolar junction transistor. This operating region of the bipolar junction transistor, it will decide the application of the transistor. As I told you that the bipolar junction transistor, it is used as either as an amplifier or a switch. So this bipolar junction transistor, whenever it is being used in active region, then it is called as amplifier. When the transistor BJT is operated in either cutoff or saturation region, it is the transistor is called as a switch. It acts like a switch there. So as I told you that earlier, so there are two junctions are there, emitter based junction, another collector based junction, So either I can apply forward bias to the emitter based junction or reverse bias. Similarly, I can apply forward bias to the collector junction or reverse bias. So therefore we will be having a three combination of this forward bias and reverse bias. In case of this cutoff region, you can say that the emitter based junction is reverse bias, and the collector base junction is also reverse bias. Whereas in saturation region, if you note out the emitter base junction, that is emitter junction, simply it is also called as emitter junction, it is forward bias, whereas the collector base junction is also forward bias. Whereas in active, right, so the both the emitter base junction is forward bias, whereas the output junction, that is collector base junction, or simply it is collector junction, it is reverse bias. So therefore, depending upon the operating region of the bipolar junction transistor, okay, so we can define the application of the bipolar transistor. As I told you earlier, that if the transistor is being operated in active region, it is right, then it is called as amplifier, or if I use the what if the transistor, bipolar junction transistor, is operated either in the cutoff or saturation region, then okay, it is called as the switch here. So if you want, I can just if you want to know the either switch here, if you try to know the circuit here, this is the logical switch. Usually we have a transistor here, okay, this is what transistor, this is VCC, this is the base current, okay, this here the collector point, what we take output at this point here, and usually Vi is applied here. So when Vi is logical 1, or when Vi exceeds this VBE voltage, this is emit base, okay, this is VBE. Usually VBE is how much? VB is, it is 0.3 for germanium, whereas it is 0.7 volts for the silicon here. So when Vi exceeds VBE, what happens? This transistor conducts. When transistor conducts, what happens? There will be a current through the transistor here, and therefore there will be a voltage drop. So if you write the output equation, you can see that VCC, this voltage, minus voltage drop across this. If I assume this as RC, the current flowing through this as IC, then it will be nothing but VCC minus IC plus RC. So when Vi exceeds VBE, it could be 0.3 or 0.7, depending upon the which transistor you use. There will be a this transistor conduct, there will be a current through this, and therefore there will be a voltage drop here, and therefore when this IC increases, so what happens? This drop will increases, and therefore this total output will decrease. So that means when I apply logical 1, what happens? This transistor conduct, output will be 0. So therefore for Vi equal to logical 1, so V naught will be 0, whereas if I apply Vi logical 0, that is nothing but, so what happens? V naught will become equal to 1. So this is how, this is in this case the transistor acts as the on switch, whereas in this case it acts as a off switch. So this is what, right. So therefore we can conclude this session with saying that depending upon the applied suitable voltage, the transistor can be either operated in active regions, cutoff region, or a saturation region. And then depending upon the the region where the transistor operates, the BJT could be used either as an amplifier or a switch.